Okay, so welcome back to the second video that is concerned with the limiting distribution of the T and the wall statistic. And for those of you who have not yet done it, they should take a look at the video that was concerned with the distribution of the T statistic. This video is concerned with the limit distribution of the wall statistic. Now the setup is the same as in the first video. We're talking about a consistent and approximately normally distributed estimator. For instance, the least squares estimator that we discussed in class, where we have a convergence in probability of the estimates to the true parameter value, and we have a convergence in distribution by the sampling error scaled by square root of n to a normal distribution. So same setup. Same setup also, the idea to estimate the asymptotic variance covariance matrix consistently, so this possibility should be given with OLS. We know that we have the term down here, which gives us a consistent estimate of the asymptotic variance covariance matrix. And we are now in the second case, in the wall statistic case, actually concerned with the joint distribution of the parameter estimates, whilst for the T statistic we were concerned with the marginal distributions down here, not so much. In this video, we take a look at the joint distribution, which we need for the walled statistic. Okay, so basic setup is the same. Make sure that you've understood all the terms, all the relationships that are sketched on this slide. Okay, so I'm scrolling over the notes that we had for the T statistic, and now turn to the wall statistic. Okay, and remember the wall statistic has as its null hypothesis a system of linear equation that is concerned with the relationship of the parameters beta, and we phrase these constraints in the forms of a system of linear equations. As a matter of fact, we have this hashtag of R number of restrictions that are phrased using this system of linear equations. Now, alternative is no, this is not true, or beta is not equal to R, or the familiar wall statistic. Now, when you take a look at the wall statistic, the basic idea is to formulate and set up a quadratic form which considers the differences between RB, where B is the estimate, the consistent estimate of beta, and the hypothesized values R. So this difference should be small if the hypothesis is true. B is a random vector, okay, of estimates. So we transpose this term and have this term again. In the end, it's a quadratic form, not transposed. And in the middle, we take the variance covariance matrix of that term, and that is R times the variance covariance matrix estimate of B, R prime, and we invert that term. So this is the wall statistic. We already discussed the wall statistic in the setup of the linear regression in OLS when we had the finite sample assumptions. Remember, and please take a look at your notes from these lectures, the intuition behind the wall statistic. Now, what we observe as from the introductory remarks on the slide is that the estimate of the variance covariance matrix of B actually is obtained by an estimate of the asymptotic variance covariance matrix divided by n. Okay, so that we can write the wall statistic in a slightly different form using the asymptotic variance covariance matrix in the middle. Okay. This is multiplied with -1, so the division by n enters as a multiplication with n when we take it out of the inverse, and I like to distribute n left and right of the middle term, and I take the square root of n, have it here, and the other square root of n I have here. Okay, nothing has changed, of course, except that I've used the asymptotic variance covariance matrix, and I have expressions which look like these sampling errors multiplied with square root of n. Now let's take a look at the terms in this expression of the wall statistic. Now, what I like to call this term in the middle, this r a bar hat r prime term, I like to call this term qn. Okay, it's an hashtag r matrix. I call this thing qn. Now, if I have a consistent estimate of the asymptotic variance covariance matrix, so a bar hat of b converges in probability to the asymptotic variance covariance matrix. Okay, what I have is that this qn object converges in probability to something that I like to call q, and that is nothing more but r times the asymptotic variance covariance matrix times r prime. And as you know, this is by the property of the continuous mapping theorem. Okay, a bar hat is conceived as a random matrix sequence. It converges in probability. Here should be a P. It converges in probability to the asymptotic variance covariance matrix of B, a matrix with real numbers. This sequence is plugged in a function, which is here R sequence times R prime, and by the continuous mapping theorem, this converges to Q. Moreover, also by the continuous mapping theorem, if I take the resulting sequence, so Qn, and plug it in another continuous function, like the inverse, I can also establish that this sequence converges then in probability to the probability limit of Qn plugged in the function, that is, I have Q to the minus 1. Again, by the continuous mapping theorem, which again proves pretty useful, right? Twice, we applied it twice to get the probability limit of the term in the middle of that quadratic form. Okay. Now maybe I'll make this a bit smaller, because I want to have a bit of space to work with. Okay, here we go. So, because now I'm going to concentrate on the terms outside of the middle term, square root of n rb minus r, these terms. Now, I can rewrite this term slightly by saying, okay, this is also r multiplied with the square root of n times the sampling error of the estimate. Okay, like this. And maybe I want to call this thing, for further reference, Zn. Again, it's a random sequence of hashtag r random variables. And of that object, I can take a look at its convergence and distribution. Now, with the sampling error scaled by square root of n, we already know that this converges in distribution to a random variable, which we call x, and this random variable is distributed normally with mean 0 and asymptotic variance covariance matrix, a var of b. So again, a var of b, that's the variance covariance matrix of the random vector x. Okay. Now, what we should note is, I said this is the same thing, But as a matter of fact, it's only the same thing if my null hypothesis holds. So the equal sign is only justified under the null hypothesis, and the null hypothesis states that r times beta is actually r. Okay, and then the blue and the red expression are the same thing. So here is essentially where my null hypothesis enters. Okay. Now take a look at the whole term, right? Take a look at the distribution or the limit distribution of r times square root of n times the sampling r by a continuous mapping theorem argument. I could also say that, maybe you write the term again, that r square root of n b minus beta, okay, converges in distribution to the distribution of r, it's not random, times x, the random variable to which square root of n b minus beta converges to in distribution. Okay, and I like to call this resulting random variable z. Okay, and the distribution of this z random variable is, well, take a look at it. X is normally distributed. You multiply it with r, out comes something that is multiplied normally distributed. Still, the mean doesn't change, and x's mean is 0, so the mean of that z vector is 0, and the variance-covariance matrix is r times the asymptotic variance covariance matrix r prime. Okay. And note that this is exactly what we've defined over there here as our Q. This guy actually is what we refer to as Q. And all this result was obtained again by applying a continuous mapping theorem argument. Right? A random sequence is plugged in a continuous function. This continuous function happens to be r times the sequence, and we can work out the limit distribution of the newly generated sequence. Okay, so that was a sort of view on how we could see the wall statistic using these random sequences. And now what we can do is we can apply one of the lemmas that we had in the script, and I think it's the lemma 6. Okay, and what we had in lemma 6 was the following. We have a sequence Zn which converges in distribution to a random vector Z, this is a vector sequence, and we have a matrix sequence An which converges in probability to a non-random matrix A, and then we're going to construct a quadratic form using these sequences, thereby generating a new sequence. And the distribution of this quadratic form is going to be the distribution of, or the distribution of this quadratic form converges to a distribution of this random variable. Okay, so that's lemma 6. Okay, now lemma 6 applied to the present context. So here, what we have is Zn, this vector sequence, being the square root of n times rb minus r. Okay, and we claim that this converges the distribution to z, and we found that this is actually the normal distribution with mean 0 and variance-covariance matrix Q. Note that I should make sure that this holds true under the null hypothesis. Okay, Here is where the null hypothesis enters. R beta is equal to R. Okay. And what AN is in the present context is, well, Qn to the minus 1, which, as we saw up there, is converging in probability to the non-random matrix Q to the minus 1. Okay. So that's the application of lemma 6 in the present context. Now, in order to figure out what the distribution is, we need to resort to a result from multivariate statistics. But let us write the wall statistic using the Zn and Qn sequences. So the wall statistic is actually Zn prime, Qn to the minus 1, Zn, and by lemma 6, this quadratic form converges in distribution to the distribution of Z prime Q to the minus 1 Z. And the question is, what is the distribution of that random variable? And if you work this out, we can work out, actually, we have worked out actually what the limit distribution of the wall statistic is, which is our objective. And this limit distribution is then taken as an approximation of the finite sample distribution of the wall statistic, and we're going to work with it. Now, in order to figure out what the distribution of that thing is, we invoke a result from multivariate statistics, a result that we already mentioned in the lecture. So we have a vector y, which is of dimension n by 1, and this random vector is distributed multivariate normal with a mean vector mu and a variance covariance matrix sigma. Okay. Then we take this vector and compute a quadratic form that results from subtracting the conditional mean from y, transposing the result, taking the inverse of the variance covariance matrix sigma, and have the d-mean vector again. Okay, again a quadratic form, and the point is that from a result from mathematical statistics, this quadratic form comes out as distributed chi-square with degrees of freedom actually equal to the number of random variables in y. There is a caveat here, which is in our case not important, but I should mention it. This holds true if sigma is a full rank. Okay. Maybe in a situation that our random vector y is jointly normally distributed, but for some reasons there may be linear dependencies in those vectors, in those multivariate normally distributed random variables. And in this case, the variance covariance matrix sigma would not be a full rank, and I would have to use a different argumentation to justify the chi-square distribution of a quadratic form. Now, in our context, however, this is not a problem. The variance covariance matrix, which we have to invert, is a full rank. It's not singular. You know. Now, what we then have is the result. It's already there. So Z actually is a random variable that is distributed normal with mean 0 and variance covariance matrix Q. Okay. We take this object here. We take the variance covariance matrix Q. We take the inverse of it. And we have our random vector Z again. So by the green result from mathematical statistics, we know what actually the distribution of Z Q to the minus Q to the minus 1 Z is. Well, it's a chi-square distribution. And its degrees of freedom is equal to the number of elements in Z. That is the number of restrictions that we phrase to construct the wall statistic in the first place, and that shows us the limit distribution of the wall statistic. So maybe we'll rewrite it again in detail. So the wall statistic, W, maybe we write it in its original form, so RB minus R prime R times the variance covariance matrix estimate R prime, invert this object, times RB minus R again. This is something that converges in distribution to a chi-square distributed random variable with degrees of freedom equal to the number of constraints. Or, if you prefer to write it like that, the wall statistic is approximately chi-square distributed with degrees of freedom equal to the number of constraints. Important to note, again, that this holds true under the H0, that our constraints are actually met. Right? If not, the derivation would fail, because look over there. At this point, we have actually inserted the or accounted for the null hypothesis. R beta is equal to R. Okay, and this shows the limit distribution of the Wald statistic. The thing to note here is that what you're going to do with that result, you're going to compute the Wald statistic using your estimate of the variance covariance matrix, which you get as described in the entry slide. You have your estimates, B, you formulate your constraints, and you get your value of the Wald statistic. And the next step is then to say, okay, you look up the quantile tables of the chi-square to find your critical values, and then therefore your non-rejection and rejection intervals, and you can compute p-values. Right, you decide as usual based on a statistic. You know the distribution of the test statistic under the null, and you decide accordingly. The thing to note here is what I showed you with respect to the distribution of the Wald statistic. It holds true and is usable for any CAN estimator. Okay, so you could consider maximum likelihood, you could consider moment estimators. We can consider something that we will encounter in the lecture and that you're going to encounter in a question for review: instrumental variables estimation, generalized method of moments, and many more. They deliver you this idea and the result that your estimator actually comes out as being consistent for the true parameter values and approximately or asymptotically normally distributed. And if you have that, and if you have your expression for the asymptotic variance covariance matrix that you can consistently estimate, you can justify your assumption that the Wald statistic is approximately chi-square distributed, and you do your test along that way. So in practical work, be it OLS, be it other estimators, people do not concern themselves too much with actually computing the F statistic that we've discussed in class, right? The F statistic came out as a version of the Wald statistic, if you like, in the specific context of least squares estimation, where we make the finite sample assumptions, in particular the conditional normality of the epsilons, the strict extraneity assumptions, and so forth and so forth. So in this context, we were able to actually figure out the exact distribution of the F statistic as a reformulation of the Wald. So there is an exactness of the distribution, but it comes at the cost of assumptions that we don't want to make. The assumptions that we need to make to arrive at the result that our estimators are consistent and approximately normal are typically much less restrictive than those assumptions 1 to 5 for OLS. And this is why modern-day econometrics rather sticks to these asymptotic results and accepts that we work with approximations of the distributions of test statistics under the null. Okay, that concludes the discussion of the limiting distributions of t-statistic and wall statistic in this video. Again, if you have comments and feedback, please let me know, and make sure that you have these derivations ready at the time when you're going to write the exam. Okay, thank you very much for listening to this video, and see you in class.